All right, we are back and we're going to talk about time temperature equivalence of polymeric materials. So remember, time temperature depends on rate, so strain rate on polymeric materials in addition to time and temperature. So we know below TG, we should expect our Young's modulus to high. As we increase temperature, we're going to see a transition from a glassy amorphous state to a more rubber elastic state. So we can kind of see that plot here of our E prime is just our Young's modulus, actually our storage modulus. We'll see that a little bit. The TM is only for a crystalline material. All polymers have a TG, a glass transition temperature. That is a second order thermodynamic phase transition, although there's some arguments about that. You could also plot the same plot as a function of time. So longer times will lead to flow, more rubbery type response. Shorter times leads to a more elastic type response as well. So this same plot looks the same if you're doing time and temperature. If I'm doing rate at very, very, very slow rates, or actually, at very, very high rates, we should see an elastic response. At very, very low rates, again, we're going to see a viscous type response. So high temperatures, long times, leads to, and basically if I look at very, very low rates, that's going to give me a rubbery type response. Low temperatures, short times, high rates, that is going to give me my elastic type response. So that's a quick way to kind of get those two concepts in your head. So those are key to remember. You can see some more plots. There's some kind of very unique aspects. If you're a crystalline material, you'll have a TM. If you're a cross-linked material or amorphous material, amorphous materials will just have a TG. Most cross-links will not exhibit that melting. Instead, you'll get basically, it drops almost nothing because you're thermally denatured. So it'll flow essentially like a liquid, but it's not a melting transition, so to speak. So that's kind of one of the key things here. So remember, glassy, again, we're changing essentially that characteristic time, that relaxation time of our polymer, and we're going to go over that. We're overcoming essentially this barriers to flow. So more thermal energy, or changing the time scale of the perturbation, you're changing essentially the dynamics of that polymer. And that will affect obviously your modulus as well. You can also basically go through this ductile to brittle transition as well, depending on the processing of your material. Again, semi-crystalline materials will have some crystallinity, and you could have amorphous materials as well, and you'll see some of these different characteristics. So next time we are going to get into one of the key characteristics of polymer, glass transition temperature. See you next time. Bye.